It's a little strange that this talk is on this day, but it's still a very fun and important talk because we're increasingly trying to deal with actual text and trying to extract value from the text. It's nice if we have structured data, but we don't always have that available to us, and we want to be able to automate the extraction as much as possible. But at the same time, you have to understand a fair amount about language and the types of languages. So when we have different languages in the world, they have different structures, different parts of speech, different rules. It complicates things. So we're going to talk just kind of a little bit about the history of natural language processing and some of the plateaus that we've hit. And then we'll talk briefly about one advance that has happened in the last 5 or 10 years to apply machine learning to natural language processing, which has increased the efficiency and efficacy of the process. I first worked with natural language processing about 15 years ago. I had a large project to help analysts find their documents. You can imagine they had 30 years of documents, roughly 42 million, I think was the number. And keyword search alone was insufficient, right? Because there's just too much stuff out there and there's a lot of ambiguity in the keywords. And so the same things that Google and companies like that have had to deal with, they want to know more about you, the person asking the question, and they want to know more about the domains that you're asking questions about. And so we were trying to do entity extraction and map them to ontologies and taxonomies and solve some of the limitations that natural language processing had at the time. And that was a useful step in this direction, but the approach that I'm going to mention has been much more successful over time and works with that as well. If you're interested, the slides are available at this URL. We'll also make sure that the Salt March team gets copies of them as well. And then my email address is at the end. If you don't find them somehow, feel free to contact me and I'll send you a link. So we'll do a quick introduction about the space and some of its history and some of its limitations. Then we'll talk about how do you go about turning text into math so that you can start to try to do some reasoning about it. And then we'll end with something called word-to-vec. It's a form of word embedding or feature embedding, which is an application of a recurrent neural network towards sequences of words. And some very interesting things come out of it, some rather surprising things as well. But I want to start off talking about my home lighting system. And don't worry, no, this is not my home. That would be a very cool home to have. This is a Philips Hue marketing image. But we've got the Hue lighting system at home, and it's throughout our house. And if you're not familiar with it, you can control the lights from an app on your phone. So if you want to set the mood or focus, turn the lights to a color and a level that will encourage concentration or relaxation, you can do all that. There's an app on my phone that turns music into commands to control the lights. So sometimes my wife and I will watch a concert on TV, and the whole house starts rocking out, and our neighbors are wondering what's going on in our house. And it's also cool, like when I get up, and I travel a lot, so sometimes I have to get up at 3 o'clock in the morning, and I can turn the lights on in the front of the house without having to stumble over things on my way out the door. So it's a nice 21st century lighting system until I can't find my phone, right? And then I feel like an idiot because I can't easily turn on the lights. So are you familiar with Tile? Is that something, do you have Tile here? It's a little Bluetooth device that you can pair to your phone and put on your keys and in your wallets and bags and things. So if you can't find something, you can use your phone to find it, but you can also use the Tile to find your phone. So I got Tile to help me find my phone so I can turn on the lights. I don't feel like any less of an idiot, but at least I get my way out of the problem. No, it was not until we got Alexa and Siri throughout the house that I think we found like the right combination. So if I'm carrying laundry or something back to the bedroom, I could just say, Alexa, turn on the lights in the bedroom. And she knows enough about the skills for interacting with the Hue lighting system and what I'm saying. It's a relatively easy thing for her to get right. And so I can refer to specific rooms, she can turn them on. I could say, turn the lights on and at 50%, set the lights to red, or whatever I want to do, right? I just interact with her. And that's a nice way of interacting with the system like this, right? It's the right combination. You shouldn't have to have something with you to turn on the lights, but just sort of like as part of your environment, being able to interact with natural language is the right approach. I also just got my wife her first new car in like 17 years, and this one has voice recognition and CarPlay, so if I text her when she's driving, she's not going to be picking out her phone and trying to answer it. The car will be able to read out the messages to her, and then she can respond as well. Yesterday, in the TensorFlow.js talk, I put a link to an example of a guy who used TensorFlow.js to interact with a camera in a browser so that you could turn sign language into commands to interact with Alexa or Siri, and then take what comes back and turn it into text so that somebody who has trouble speaking or hearing could interact with these kinds of systems as well. Now, not every system or not every environment in the world is going to work well. Like noisy environments or at work, I don't anticipate voice is going to be a huge impact, because you don't want somebody yelling out like, remove all my files, right? No, not on my computer, right? That's somebody else's computer. But for cases like this, being able to interact with the environment through just natural language is a very convenient approach. And it's a very complicated problem, because even before we get to the processing of the text, when I say something, my mouth moves, it compresses air, the air will move a microphone, the microphone will generate voltage, the voltage is turned into a series of signals. We interpret those by decoding them into a series of phonemes, putting them back into words, and then analyzing the structure of the text at that point. So it's a very complicated process, and we're not going to touch upon all of that, but we'll talk about how some of the advancements have affected the different parts of it. So we generally use natural language processing for search and retrieval. Historically, if you needed to search an information storage system, you would have to write a very complicated technical query. Even like my mother-in-law is a librarian, and she had to learn regular expressions and crazy things just to do complex queries across all the books and magazines and things that they had in the library. And in order for that to be successful, you have to know something about the nature of the domain that somebody's asking about, right? And so that's naturally how Google has evolved to be able to say, find me pictures of ponies, right? And that's not how people have historically worked, and they've now kind of ruined it for everybody, because if you have an information system, everyone's going to want to interact with your information system the same way that they interact with Google. So that's why it's a good time to be learning some of these things. In the process of doing this, though, we have to be able to refer to entities and have them know what it means. If I said something like, I asked Michael Carducci to bring his copy of Season 5 of Game of Thrones to me in this room in SD Hall 1, if you make everything explicit, it's pretty easy to match those patterns. But if I said, I asked him to bring it to me here, right, that's a very much more difficult process. You have to figure out what do those references mean. So we need to understand what entities are being referenced and how do they relate to what else is going on in the text. You need to know something about the linguistic structure. What is the subject of the sentence? What is the verb of the sentence? That helps us with direction, causality, who's doing what, those sorts of things. And obviously we want to work with machine translation. I lived for several years in Japan and Germany, and I studied both German and Japanese. I'm also learning Spanish now, and I travel a lot, so I'm often in hotels, and I don't really have anybody to talk to. So I like the fact that Google Translate can basically check my pronunciation on something. Like, if it understands me, I think it can't be that bad, right? So machine translation has gotten very good in the last several years, in part because of some of the advances that I'm going to mention. One thing people don't think a lot about is not the parsing of natural language, but the generation of natural language. Particularly for documentation of business processes and things like that. That's like the worst kind of documentation to write, right? Nobody wants to write it, but it's important for people to understand the process. You can imagine if you had a sufficiently rich model of a business process, you could then spit out and say, this is a 12-step process, and the first process takes in a document and then normalizes it into some form. You could generate text from a model. And that's becoming an increasingly interesting thing for places where we just simply don't have enough people to write copy or content to describe our systems. But the biggest real issue is question answering, right? This is a big part of systems like Watson, but even just Alexa and Siri, being able to ask questions When was this movie made? How tall is this person? Where was this person born, right? That kind of thing is just a lot of fun to have as part of our lives without having to stop and get the computer out and open things up. Also, sort of like, we have two little dogs, and they like these dental chews that keeps their teeth clean. And every once in a while, I'll notice that they're running low. And rather than having to get my computer out and go to Amazon and place an order, I could just say to Alexa, hey Alexa, reorder the greenies. And she connects the word to my order history and is able to make that part easy as well. In the 1950s, people like Terry Winograd had systems called, like a system called Sherdlu, which was a funny name for how his keyboard was organized. But if you think back to what somebody might have thought about seeing an interaction like this, they would have been blown away, right? So if a person is talking to a computer through text and says, pick up a big red block, and the computer says, okay, grasp the pyramid, I don't understand which pyramid you mean, and then the person changes their mind and says, find a block which is taller than the one you're holding in it and put it in a box. By it, I assume you mean the block which is taller than the one I'm holding, and the computer says, okay. If you looked at this interaction, you'd be surprised, and it would seem like the computer understands what the person is saying. But the reality is, in this scenario, there's only so many scenarios that could unfold, right? There's only so many objects, there's only so many types of interactions. So the programmers were writing rules, and the rules would anticipate what somebody might say, and then tries to match the rule to some kind of response. And that, works for about 10 minutes, and then it's not all that interesting, right? And I remember as a kid playing around with variations of like the ELIZA program you may have played with, where it seems really cool for about 10 minutes, and then you get really bored, right? Because you can find the edge cases of where the programmers stopped anticipating the rules. Although one of my favorite experiences, there was a toy that I always wanted but I didn't have, and one of my friends had. It was called 2XL, and you'd plug these cartridges in it, and this didn't have a speech recognition mechanism, but it serves a purpose with respect to the anticipation of rules. So there were buttons you could push to interact with it, and you'd put cartridges in, and it would say, do you want to play a game or do you want to learn something? And you'd push a button, and then it would respond to that. So again, my brother and I would play around with this, and after about half an hour, we'd get bored, and it would say, press A or B, and we'd push C. It says, that's not a valid response. Please press A or B. We'd push C. That is not a valid response. Press A or B. We'd push C. And it says, either you're not very good at following directions, or you're just trying to figure out what I would say. We're like, ah! It was only when I became a programmer later in life I realized that was probably just a programmer who had kids, right? And knew that there was going to be an abuse rule, and they figured out how to plan for it. But it was not until the 1980s that we shifted into what was more of a probabilistic model rather than a rule-based model, that we started to see some real advancements. And so some of the early stuff that I'm going to show you basically comes from that kind of time period. And it's amazing how easy it is to get pretty good results, but then you're going to hit a plateau based on what's possible with those kinds of systems. Now, some of the complexities, you have to understand if this is encoded text on a computer, you have to understand what encoding. Is this ISO 88591? Is it UTF-16? Right? Before you even try to turn it into language, you're going to have to figure out the right way to parse it. You're going to have to figure out how to break it up into tokens, sentences, words in the sentences. Obviously, some languages are left to right, some languages are right to left. So different languages will have different rules. You'll have to know how to label parts of speech. You'll have to know how to turn words to and from their stems to connect them to their past tense form or their plural form. Sometimes you need to understand like what's the fundamental meaning of the word, the lemma of the word. So the lemma of the word operating would be operate. And the detection of the boundaries with sentence and paragraph helps us establishes where is it likely that we will have come across the reference. So if I said, I asked him to bring it to me here, I will have had to establish who he is at some point, and usually looking in paragraphs around there can help us with what is ultimately the hard problem of co-reference resolution. When I make a reference to something, how do I know how to resolve it so that it's specifically what I mean? And you can imagine, interacting with modern systems, like you said, send one Bitcoin to somebody, and then it goes, and you're like, oh, no, not that person, the other person, Bitcoin doesn't allow you to take it back. So you want to make sure that you've got the reference correct before you act upon it and delete somebody's files or send them something, right? Now, there's a lot of open source tools out there. Many of these are Java-based, and many of these have support for pipelining, because a lot of times you're going to want pipelines of processing of this data. Many of these support multiple languages, but the thing that I like about this, though, is how rich and varied the open source versions are. Because 15 years ago when we were doing this, and keep in mind, we were trying to parse 42 million documents, and based on the hardware that we had available to us, that would take approximately a year. So we wanted to do this as fast as possible, and some of these commercial entity extractors would say, you can use one thread. If you use 2 threads, we're going to charge you an additional $20,000. And so I'm very happy to see that there are open source versions of these things now. Every one of these, I think, could be of interest to you, but I also wanted to point out, I obviously, unfortunately, I'm not familiar with Indic languages, but I found a library with a link here that has some really cool capabilities and some Jupyter notebooks that you can play around with if you have Python and a couple of the other dependencies installed. And that helps dealing with some of the complexity of the different input methods and the different ways of representing characters between various Indic languages. And so I think this might be something of interest to you as well. So you can see, how do I normalize the different references of the characters between different languages? How do I convert scripts from one to another, so from Hindi to Tamil? How do I Romanize those? Those are all things that might be useful prior to trying to do some natural language processing on those. So I leave those links in there for you to play around with. I'm going to do so as well, but you may have more pressing need than I do. But the trick is, how do we turn this into math? Right? How do we turn text into numbers? Because ultimately that's what we're going to have to do to rely on things like machine learning and help us find these documents. And so the vector space model was one of the early moves in this direction. And as we see, there's not a lot to it. Imagine if these were 2 separate documents, not very interesting documents, admittedly, but the first one says, John likes to watch movies, Mary likes movies too. And the second document says, John also likes to watch football games. So we call a collection of documents that we try to learn from a corpus. It's just a collection of documents. And we look at the words that are in those corpuses. And it's important to think like this because obviously a collection of books for targeting children is going to look very different to a collection of graduate research textbooks or something, right? So if we're trying to understand what's expected or likely or the terms that are mentioned in a collection of documents, it's important to know, like, how do those documents relate to similar documents. So one of the first things that we can do is just to go through and look at every word that's unique across all the documents in the corpus and turn it into what we call a bag of words, right? It's just a set of unique words, and then we can encode a single document as a vector that indicates whether that word is in the document or not, or possibly how many times it's in the document. I'll come back to some of those discussions in just a second, but I could now represent the first document as 121120000011, right? Because John is the first word, and John is in the first document once. The likes is the next word, that's in the first document twice. So I can imagine representing this collection of documents with these vectors. But we've lost something now. What did we lose here? The order of the words, which is going to give us some notion of context and directionality and those sorts of things. So it's very simple, but we're giving up some context in the process. To maintain some of the context, we could use a slightly different model called an n-gram, and it's a small number of words. So in this case, a bigram would allow us to say John likes to watch movies, Mary likes, right? Those are some amount of context. And we could kind of think of bag of words as just an n-gram where n equals 1. But we don't want n to be too large, because then we're going to start to get into the space of entire sentences, and those are going to be less likely from document to document. So again, this is a knob that you might turn to say, like, what makes sense for this document corpus versus another document corpus, and this can help us with that. So we can maintain some of the context, but obviously not much of it. But the amazing thing is, just with these simple ideas that we've just expressed, we now have the ability to represent a particular document, right? Document J is really just a collection of indications of whether a particular word is represented in that document or not. And I can imagine a query as being a similarly structured vector. So if I want to know if the word cat is in a document, I could put in my query the word cat. Or if I want to know if the word banana is in my document, then I could search for wherever the word banana is supposed to show up based on the n-grams or the bag of words. And now it becomes just a simple math problem. Euclidean dot product is a way of measuring the similarity between the vectors, and the vectors become these high-dimensional spaces based on the words and whether they show up in particular documents. So if I rearrange the equation, if I look at the cosine of the angle between the dot product and divided by the normalization of the vectors, this gives me a sense of how similar two documents are. But it also gives me a sense of how similar a document is to potentially a query, right? So now the query vector, obviously we're talking about much higher dimensional spaces, but whatever documents are closest to the vector are going to be the ones that we're going to want to bring back. And so I can now compare a query, this is more like this document, more like that document, or this collection of documents are kind of in the same space. This is a very simple way of trying to build a document management system. And most of the document management systems you may have used over the last 10 or 20 years will have something like this as the basis of the approach. So if I look at two documents and the cosine of the angle between them is 1, then they're the same document. And if the cosine of the angle between them is 0, then they have nothing in common. For most documents, it's going to be somewhere in the middle, but this now gives us the ability to find clusters of related documents relatively easily. I mean, if you sat down and tried to build a document management system just with what I've told you so far, you'd get pretty far along to doing something interesting, right? Now, what do we put in the vectors? One of the things that we could do is we could say the term frequency of term T in document D is either a 1 or a 0. Just is it there or isn't it there? And what that does for us is that limits the sense of how important the word is to the document, right? If I have a document that just has the word banana in it once, like, hey, I once ate a banana, that's probably not all that important to the document. But if I have like a cookbook that shows you all the kinds of different ways you can use the word, or you can use bananas, obviously that word is going to show up there a lot of times. And so just indicating whether it's there or not kind of loses some amount of the impact of how important the word is to the documents. So I could turn around and say, all right, well, if I encode in the vector not just a 1 or a 0, but a count of the number of times the document's in there, then the frequency of the term in the document might show up as well. This would measure the difference between just casually mentioning a word and focusing on that word like a banana cookbook. But it also is then going to favor longer documents, because longer documents are going to have higher counts. But it's also going to favor words that show up a lot. So like articles, the, of, an, right? And those aren't interesting words to search for because every document has them. So there's no right answer what to put in the vectors. It's going to depend on the nature of the text, the nature of the business problem, and people come up with all kinds of crazy solutions, like start with 0.5 and add 0.5 times the frequency of that term in the document divided by the maximum frequency of any term in any document. So if a word shows up 10 times, that might sound interesting, but if there are other documents that have a word in it 1,000 times, then 10 is not a very big number. So again, these are just different approaches that people have had to try to come up with things that work in general across a range of documents. Now, they came up with a cool way of trying to deflate the impact of very, very common words. And that's called inverse document frequency. And it's the log of the number of documents that you have divided by the number of documents that have a particular word in it. So if the word the shows up in every document, then that's going to be n over n, which would be 1, and the log of 1 would be 0. So it's just a way of saying, you know what, that's not an interesting word to search for. So you can imagine combining these two into a multiplication. Either a word shows up a lot, and it's important to the corpus because it only shows up in a couple of places, or a word shows up a lot, but it's not that important because it shows up everywhere. And these are like two different levers, but it basically gets us a nice balance of which words frequently and are interesting in a corpus. So in a technical manual, set of technical manuals, computers or modems or routers or domain terms might show up a lot, and they could be very relevant to the topic at hand. But this would then deflate based on the very common words that show up everywhere. So as an example, we have two weird little documents here. One, this is a sample, but the word shows up twice there, so there are 5 words in the first document. And this is another example that another shows up twice, and example shows up 3 times, so there are 7 words in the second one. If I look at the term frequency, 1 out of 5 words is this in the first one, and 1 out of 7 words is this in the second document. So trying to compare 0.2 to 0.14, it's kind of hard to tell whether that's useful or not, that distinction. But if I look at the inverse document frequency, I'll see that it's 0 because the word this shows up in all the documents in my admittedly small corpus. So if I combine these two, we'll see that one comes out to 0 and one comes out to, the other one comes out to 0 as well when they're both not important to the corpus. But if I search for the word example, it doesn't show up in the first one, it does show up in the second one. The word is more important to the corpus because it only shows up in one of the documents. Therefore, I can now start to segment. That word is interesting to the corpus, but doesn't show up everywhere. So the second document would be a more important one to return to. So this is how fundamental information search and retrieval and document management based on keywords works. And it's this kind of combination of levers that have been put in place. So it works remarkably well, but we run into some fairly big limitations. If I have a document with the word dog in it and I search for the word dog, I'll find that document. If I have the word cat and I search for that and it's in another document, then I'll find that document. But if I search for the word animal, I will find neither document because this system doesn't allow for relationships between terms, and that's a big part of the nuance of human language. So these systems would get us only so far, but they wouldn't handle synonyms and polysyms and words that have multiple meanings. And so that's a problem, and that's why we hit these limitations in the 1980s and into the 1990s. Now, there's some fundamental aspects of linguistics, though, that have been around as linguistic theory since like the 1950s. And one is called the distributional hypothesis of the semantic theory of language. It's a very fancy term, but it basically means words that are used and occur in the same context tend to mean the same thing. Or more colloquially, a word is characterized by the company it keeps. And that's something that we can start to exploit. Now, this very simple vector model approach that we've talked about does not allow for much context to be maintained, so obviously we're going to lose some of that. But when we think about how we could represent sequences of words and then turn them into linear algebra and then try to build these high-dimensional vectors, hopefully there's some way that we could deal with that. Now, obviously if we have very large corpuses and we have lots of words in them, these are going to be very, very, very large vectors and require a lot of computation to try to do anything with. But here's where it starts to get kind of interesting. Because we can leverage the similarity of words. One place where words are similar is if they show up in the same part of a document. So in terms of scientific research, we generally have abstracts at the beginning of an academic paper. And that's the important part there is it's distilling what are the important concepts in the document. So if the same word shows up in 2 different abstracts, then that is probably a stronger relationship between those documents than if the words showed up in the rest of the document. So the structural or textual region that a word shows up in has some implications in terms of its relevance. There's something called paradigmatic similarity, which means if I could swap one word out for another and not change the meaning of the sentence, then that's interesting because those words can now be used interchangeably. So if you went to an elementary school and you said, hey kids, how high can you count? And somebody said, I can count to 10. Somebody says, I can count to 20. Somebody else says, I can count to 30. Somebody says, I can count to banana. There's always one, right? The words 10, 20, and 30 have paradigmatic similarity because swapping them does not change the meaning of the sentence. But obviously the word banana does not because it changes the meaning of the sentence. So paradigmatic similarity is what word can be swapped out, but that then implies a connection between the words. Something else we can do is look at the sequence of words, right? The symptomatic similarity basically says what words combine. So I could say the man cried, the boy died, the boy sang, the man sang. Those are all kind of combinations that we could say structurally, but we would analyze the combinations of words and how they come together on the symptomatic axis, and we could imagine which words can be swapped out on the paradigmatic axis. And so if we start to be able to leverage this kind of understanding in some kind of vector representation, then this may be something we can start to do some more interesting stuff with. And so in the late 90s and early 2000s, there were some attempts at this using something called latent semantic indexing, latent semantic analysis. And it tried to take common terms like vehicle, car, and van, put them in a document term matrix and find a lower dimensional representation of them. Because we're saying, look, we don't really need to consider the difference between a car and a van and a vehicle with respect to trying to find documents that are related to those. And so this was an attempt to leverage the relationships between words, but it also allowed us to start to think about, okay, well, the word neko in Japanese and the word chat in French mean the same thing. So I could do some matrix manipulation and then try to do some cross-language query. So you could query text in one language, but have the actual text be in another language. Unfortunately, that approach didn't scale very well. All right? When we're now talking about web scale systems, we needed a new approach. But here's where things really, really start to get interesting. Because imagine I've got the capacity to represent this stuff somehow. These vectors are very large, and we're not very good at visualizing things more than about 3 dimensions. So I don't know really how to look at high-dimensional vector spaces, but there are dimensionality reduction techniques like T-stochastic network embedding, which is just a fancy way of saying, take a high-dimensional vector space and compress it down to 2 or 3 dimensions, so us with our puny brains can kind of see what's going on. And if you do that, we start to notice things like, I'm sorry, it's kind of hard to see up here, but I'll tell you, the months of the year show up together, and the days of the week show up together. And notice Monday through Friday show up more tightly connected than they do with Saturday and Sunday. They're still in the same neighborhood, but they're slightly different because we talk about weekdays and weekend days slightly differently. Right? Everybody says, I'll see you Tuesday, I'll see you Thursday, I'll see you Sunday, but nobody says, thank goodness it's Monday, right? I don't want to go to work today. And so this is kind of interesting, right? Because this clustering is something that we can exploit just by looking at how words are used together. And this is the basis of the big shift towards this new approach called word embeddings. So before we leave the vector space model just on its own, it's a very useful and simple, fast way to get going. We can use linear algebra to talk about these things. We can represent things with binary weights or non-binary weights. We can find ranges of documents that are similar. We can order them to find which ones are more relevant. These are all good, useful things, but long documents tend to be poorly represented or overly influential. The words that we search for have to be exact. We're just using them as kind of like indices into the vectors, into the document space. Synonyms get lost, right? If I search for the word hand, right, there's multiple meanings, like give me a hand, I have a hand. Those would return unrelated things, and we would have to let the person asking the question then resolve what's interesting and what isn't. Or if I use the same, I'm sorry, in that case, with synonyms, if I said one word, dog, but I meant animal, I would lose words. If words have multiple meanings, then I would get back too much information, right? So these are some of the limitations that we were running into in the late 80s and 90s. We were losing the term ordering, given how important things like symptomatic and paradigmatic similarity is. That's a lot to give up. And that's where things like word2vec show up. This was based on some work by somebody who was originally at Microsoft but then moved to Google. And it's an approach to encoding a sequence of states that are related to each other. So this is, word2vec is just one form of this. There are other ones like gene2vec, where you could analyze genetic sequences and say which of the base pairs and everything sort of co-locate together. And you could start to say, okay, well, based on this sequence of genes, what would we expect to come out after it? So there's a whole different combination of approaches that we can do here, but we're going to focus on the word aspect of this. So generally, we want to look at the sequence of words with a sliding window of context, and we have a word, and then we see what's around it. So it was help us define which words co-occur, and you can imagine something like the Soviet Union, or New York City, or Elon Musk, right? Those words would show up often, but Soviet banana would not, right? And so this gives us a sense of the likelihood of words to co-occur. Now we would need a way of representing the sequence, and that's where this approach leverages recurrent neural networks. So we can have networks that capture sequences of events as a series of relationships. So in this very simple model, we could have an input vector representing what's called a one-hot encoded format of all of the words. So if I have a particular word that I want to look for, then that position will be a 1 and everything else will be a 0. But then I can start to say, all right, how do I represent that in some kind of smaller hidden layer? And ultimately what I want to come out at the other end is, of all the words that I know about, what words are likely to be co-occurred with the input word. So we're building up a probabilistic model as a series of sequential analysis of contextually related words. Now, we have, say, 10,000 words maybe. We have 300 neurons in our hidden layer. We're finding ways of encoding the weights of the importances of the co-occurrences between these. But I can then use it as a lookup into this table of what's the most likely word to come out the other side. Now, I guarantee almost every single one of you have benefited from this. If you're texting on your phone and you say, hi, how are, and the word you shows up, that's the most likely next word based on the documents that it was trained on. But that's also useful for things like speech recognition. If I say, hey Alexa, remind me to send her the farm. She could say, I'm sorry, could you repeat yourself? Like, did you say form or farm? Instead, with a word2vec embedding model, she could say, like, nobody says send me the farm, they say send me the form. And so it could be used to disambiguate things like that. Or for optical character recognition, if you don't know, hey, I didn't quite catch what that word is, this kind of model would be useful for that as well. So we end up with these input vectors that are selecting the weights of the rows, but these weighted rows represent then the vectors associated with that word. And here's where it gets really weird. So we take, say, the word vector for ants, we then compare it to the word vector for car, and we can use an output layer called a softmax regression. It's just a way of saying, of these opportunities, which is the most likely one. And it would then tell us the word ants and car don't show up very often, right? The word ant and hill might show up. The word ant, I can also start to see which of these vectors are similar, right? So the word ant and ants would be very similar. The word walk, walking, walked, walks will have similarity as well, but we'll also see things like, oh, I went for a stroll, I went for a walk. So the words stroll and walk would have close similarity, cosine similarity in the vectors that were generated as well. So we can now, this is how we can start to find these relationships between these words, and not only are we getting this probabilistic model about sequencing and what's likely and that, but also finding the connection between these words. So why is this interesting? I apologize, in the published slides that I had, there was an old link that didn't work and I didn't realize it until after I'd submitted it. So this is a Java-based deep learning environment called Deep Learning for J. There's nothing special about it, it's just I like the way they present this word2vec situation. So not only do we have this probabilistic model that comes out, it also allows us to discover Scandinavia. You might say, what are you talking about, Brian? Well, if I look at the cosine similarity between the word Sweden, I'll see that it is closest to Norway, Denmark, and Finland. And that's because people talk about Scandinavian countries the same way, because they have similar cultures, similar weather, similar food, similar geography. But it also allows me to see that, the way people talk about Sweden is more like how they talk about Switzerland and Belgium than it is, say, France or Greece or Spain. Again, we're talking about different foods, different cultures, different geographies, different weather, right? So it's just the words we use to describe something help us find the semantic connections between things. And that's a fascinating concept, right?
So we are running this model on, let's say, a lot of text data, right?
Mm-hmm.
And it would find a lot of things which wouldn't even make sense, right? And some things which would make sense like this. How do we segregate those things, right?
Well, the things that won't make sense are generally going to be further away in terms of cosine similarity. So you'll set a threshold, right? There'll be some kind of threshold by which you'll say, all right, don't show me anything more than anything within this. And I'll show you an example in just a second that allows us to do that kind of thing. So not everything that I'm about to show you necessarily is going to always be the case, but there's some very interesting insight that comes out, such as that the words in different languages end up in the same place. And so I'm sorry you can't read this, but this is 2, 3, 5, 4, and 1. And that's very similar to cuatro, cinco, tres, uno, dos, right? Because in Spanish, we use numbers in the same way that we do in English, in the same way that we do in Japanese. But at the same time, horse, cow, pig, dog, caballo, vaca, cerdo, perro, right? We talk about animals the same way in different languages. And so this is how we've been able to improve machine translation, because when you basically try to do a translation and it's not entirely sure what you're saying, or it may not know that word, but it's got some kind of corpus to learn from, if the vector space that you end up in is similar to a similar word in a different language, then that's probably a stronger likelihood that that's what you're trying to meet, right? So that's a very fascinating result that comes out of this. But we also start to see that the relationships between words show up as well. So the relationship between China and Beijing, and Russia and Moscow, and Japan and Tokyo, the size and the shape of the vectors are similar between those, because we talk about countries and capitals in the same way. Now notice Turkey is also a bird. And so if the corpus has references to Turkey the country and references to the bird that's a turkey, that will impact, obviously, the shape of the vector, but notice it's still roughly in the same space. And so now think about this. If you had some kind of understanding about the fact that Berlin is the capital of Germany, but you go back in time to, say, 1988, in that case, Bonn was the capital of West Germany. And it wasn't until reunification that Germany now became reunified Germany and the capital of Germany became Berlin. But if we just simply analyze the news stories over a sufficiently large period of time, we would start to detect that. The shift from Bonn being the capital to Berlin being the capital, because the vectors between the words would start to fit in a more similar pattern. And so now this is a fascinating way of looking at how things change over time. You can now imagine going back through scientific literature and saying, well, how did we talk about infectious diseases before we invented antibiotics, right? Absolutely fascinating what might be mined through that kind of historical analysis. But we can also start to think about analogies. And these analogies are very unpredictably a function of manipulation of vectors. If you have the vector for the word king, and you subtract the vector for the word male, and you add the vector for the word female, any guesses where you end up? Queen. Because to the extent that we talk about monarchs differently, gender is often one way that we talk about them differently. And so we have a whole series of kind of interesting results. If you take the vector for the word Iraq, trained off of the Google News corpus, and you subtract the word violence, you end up in the neighborhood of Jordan. And that's kind of a weird outcome until you stop and you realize Iraq and Jordan were two countries created about the same time in about the same place for about the same reason, similar culture, similar religion, similar food. But Iraq has been involved in more wars than Jordan has. So if we remove the impact of violence and words that relate to violence, which will then cluster together, from how we talk about Iraq, it's not surprising that we would end up in the neighborhood of a similar country. Or, I like this one, president minus power equals prime minister. I'm not really sure what to do with that. Or library minus books equals hall. Right? If you take the books out of a library, then it's really just a place to go and hang out or walk through, right? Or the word for stock market ends up very similar to the word for thermometer, because both are very complex systems that we're distilling down to a single measurement. And that's, again, this is absolutely fascinating, because ultimately, this is an unsupervised learning result. Most of what we do with machine learning is supervised learning. And this is just looking at the sequences and the context and the orders of words based on how people use them, and we're able to find these semantic relationships between them. So this is one of the reasons why this has gotten so much better in the last couple of years, is because we can see these connections between these. So let me show you a quick example. Pretty much any machine learning framework of note will have some kind of word embedding support. Those NLP frameworks that I listed earlier don't have a lot of machine learning stuff in them. They have support for part of speech tagging and tokenizing and things like that, but they don't have things like word Tyvek or Bayesian classification yet. I think they will in the near future, but right now you have to go to a machine learning framework to get these sorts of capabilities. So in this case, we're going to pull in a file, which is just a collection of raw sentences, one sentence per line. And if I show you the sentences here quickly, there's nothing special about them. It's about 3 megabytes, 2.5 megabytes. That was less than a year ago, but he made only the first. There's still time for them to do it, but he shouldn't have, right? There's nothing ordering these in any kind of way. But if I then read that in, pull in a basic line iterator, so this is going to iterate over one per line, and then I'm going to tokenize it using default white space tokens and punctuation. So this will be language specific. If you have a language that tokenizes differently or doesn't tokenize, you'll have to use a different tokenizer. But we have a tokenizer factory interface, and for English we can use the default tokenizer. We've got a common preprocessor to strip out numbers and common words and things like that. But in the end, I can build up my word Tyvek implementation by just calling this builder. So we've got a builder interface here. We can say, only include words that show up at least 5 times. How big is the hidden layer? What's the window size of the context that you want to slide over, and iterate over it, and then build it. At that point, we can then fit the model to our training document. It will go through and parse it, and this takes a little while. And then you could save this out and load it back into your production runtime system if you wanted to. So we're just going to write it out to a text file. But once we have the model, we could then say, find me the 10 words closest to the word day. Now, how much domain-specific knowledge have I written here? 0, right? It doesn't matter what this text is. This could be medical text, this could be news stories, this could be tweets. But what we see is, if I run this, and I'll read out what it says. So, okay, it's loading it up. It's building the vocabulary. This obviously takes a little bit of time. And so you wouldn't want to do this every single time. You would do it and write it out, and then in your production system, read the model in. But once it's there and we're done building, we can say, find me the 10 words closest to the word day. And with no specialized handling, no supervised learning, it comes back and says, the closest words to the word day are night, week, year, game, season, time, group, and then it gets a little weirder. So to your question, right, these past a certain threshold, it's not all that interesting, but the fact that with no domain knowledge, no specific understanding of what the text is there, no ontology or taxonomy that we're trying to match against, we can find that the word day correlates with night, week, and year. And that's fascinating, right? Because now, if somebody searches for something and you don't find any results immediately, you could say, okay, take the words that they searched for, find similar words, and try to search for those words instead. And now we can combine the vector space model with an understanding of the relationships between words to help find related content that's more amenable and friendly to the person asking the question. So this is just one example. There are a lot of things that are happening in the natural language processing space, like Bayesian reasoning helps us do document classification for the identification of spam, but the exact same math would allow us to turn around and say, let's do some sentiment analysis, right? Maybe you have a social media team and they only have a certain amount of time to spend, and you want to respond to the most important tweets that mention your company. If people are saying good things about you, you don't really have to engage much, right? You could just say, all right, well, this was a compliment. Let's pick from a handful of, a couple of dozen responses and just randomly pick one. Hey, thanks for writing in. Great, glad to hear it. Let us know if we can do anything else, right? So if you can use the same Bayesian reasoning to determine whether something is a complaint versus a compliment, right? There are going to be certain words that would correlate more with one than another, right? Suck probably isn't a compliment, right? And so then you could say, all right, well, those things that we identify as compliments, we can just automate a response to. The things that are complaints, we're going to want our social media team to say, sorry to hear that. Can you tell us what happened? And try to engage more. Imagine that you have a Jira backlog, and it hasn't been categorized, right? You don't know what's a feature versus a bug. There are going to be words that are going to correlate with something being a bug, and there are going to be words that correlate with something being a feature request. And so you could take a stab at automating classification of your backlog. And so the math works out the same. So what we're finding is we can leverage our understanding of human linguistics, capturing sequences of words, discovering semantic relationships between them, and then combining this into probabilistic reasoning for document classification purposes, for making user interface improvements so that people don't have to type everything in the whole way. These are all improvements that are happening in the natural language space, and part of why it has gotten so much better in the last couple of years. So I'm going to end there. Here's my email address. Feel free to contact me if you have any questions. I'll go ahead and put the link back up if you want to grab the slides. But as I said, I'll get them to the conference organizers as well. We've got time for a couple questions, if there are any.
Can you talk more about the supervised learning?
Yeah, I'll spend more time talking about that tomorrow, on Thursday in the machine learning architecture talk, and then we've got the workshop on Friday. But the main difference between supervised and unsupervised learning is if there's some kind of what we call ground truth that you're trying to learn. So if I'm trying to find what makes somebody a good candidate to loan money to, it's probably not going to be their favorite color, right? Unless it's blue because those people are awesome, right? But your income, your debt levels, your risk tolerance, those are all things that could correlate with the outcome of paying us back or not paying us back. So if I had decades of loan history, then the supervision comes from that data to help me find what the connection between these inputs and outputs are. But here, I'm just looking at text. There is no ground truth. There is nothing driving the process other than how do these things cluster based on usage, and that's why it's an unsupervised activity. Correct. So historically, we have had to do all the feature selection and engineering to find what's important and then train off of it. More advanced environments like deep learning systems can automate some of that, but you have to have substantially more data in order to do so.
Have there been any successful approaches to detecting things like sarcasm?
Yes, the question is, have there been successful approaches to detecting things like sarcasm? So I said earlier, if somebody says, you guys suck, right, that's probably not going to be a compliment. But if somebody says, hey, that was great. Oh, good, glad to hear it, right? If you can't detect sarcasm, then you're going to annoy the person even more. I will say there have been some advancements, but it's not widely used and it's not super popular. So to the extent that companies have developed solutions or research organizations have developed solutions, they tend to be fairly proprietary and as far as I know, not widely used. But I think we'll start to see things like that emerge into the open source space in the not too distant future. Right.
But then there is another thing is like, if they're finding an ED in a paper, now that's there is correlation we need to, but in a very different context. So like, yeah, how do we quantify those?
Right, so the question is about idioms, right? Sometimes we say things like, oh, I've got a frog in my throat, or, you know, nobody actually says anything about needles and haystacks unless they're making the idiom. If it's not sufficiently widely used, then it would be hard to find evidence of that, but because it is such a common idiom, it would still show up, right? So in that sense, even though they normally wouldn't be connected conceptually, because of the idiom and because that's a popular idiom, we would end up finding that relationship as well. And to try to determine whether it's an actual structural thing or an idiomatic thing is probably going to rely on more domain knowledge about the language itself. So. So how to get started? Is that your question, is how to get started? Yes, so it would, why don't you send me some email, and I'll try to answer that, because it's going to depend on what kind of environment you're working in. You know, if you're talking about like a Java-based environment, my answer might be one thing. If you're talking about Python, well, so the NLP toolkits that I mentioned are all Java-based, and they all have tutorials, and they all have things like tagging parts of speech and doing entity extraction and things like that. So I would say go look at the links that I gave you, and that will help. If you want to play around with the Indic language support, that's Python related, but it's also got good examples, and I think either one of those two would be a good place to start. Uh-huh. Correct. Let me shut down, and then I'll be happy to talk to you offline. So thank you very much. I appreciate it, and enjoy the rest of your week.